So in the first video, we talked about how computers use what's called a frame buffer to draw graphics. That is, there's a series of pixels left and right across the screen and up and down, a grid, and each of those pixels corresponds to a location in memory, video memory. And the computer will just write the colors, turn on the pixels at the colors that they want by simply writing values to specific memory locations. So if you wanted to draw something, one of my favorite video game characters, it's Burger Time. This is Peter Pepper from Burger Time, one of my favorite video games ever. And this is what it looks like if I drew the pixels out and blew them up so I could, see the pixels. This is what it would look like. Okay? And you can see there are 16 pixels across, 16 pixels down. So just to draw this guy statically, let's figure that out. How many writes is that? Okay, 16 times 16 is what? Oops, that's not right. 256, right? So just to draw this guy on the screen in a static position, it's going to take 256 write operations, writing something to RAM. That doesn't even include actually getting the data from wherever it is, on the video ROM chip or the graphics, get it to the CPU and then putting it to the memory. This is just assuming the CPU already has it, writing it to data. Okay, and then if we wanted to animate him, how would we animate him? Well, to animate something, let's say we want to move him right, we would actually probably change his what he looks like. He might maybe moving his arms or his legs, but just let's say we're just going to move the static image right. We would have to shift everything, rewrite all these 256 bytes, but just one position to the right, and then we're going to actually have to write another 16 bytes to kind of erase where he was. So 256 plus 16, 272 operations, write operations, just to move him once. That's once, one pixel. If we're trying to make a smooth animation, we might do this multiple times a second, maybe 30 times a second. So let's assume 30 times a second. We now have 8,160 write operations just to move Peter Pepper 30 times a second. Okay. Yeah, not a big deal, right? That's not too much. Computers can handle that. Well, what happens though? I mean, are all we doing is moving Peter Pepper? There's probably enemies like Burger Time, pickles and hot dogs and eggs. And what else is there? Is there French fries? I don't think there's a French fry. But there are French fries, but they're not bad guys. So there's characters chasing him. So let's assume there's 16 total sprites on the screen. This is called a sprite. So there's Peter Pepper and 15 bad guys that can be on the screen. So let's multiply this by 16. All right, well, we got 130,560 operations just to animate these guys, not including background, drawing the background, not including actually doing the logic to figure out what are they doing, what has Peter Pepper done? Has he scored some points? Has he picked up a pepper? Has he thrown a pepper? It's not doing any logical operations. It's just drawing these guys. And what's more is, let's say on a 6502 that to write something from the CPU to RAM, to video RAM, takes 6 cycles. Or let's just say 5 cycles. Let's just say 5 cycles. I don't even know how many cycles it is. It's like 5 or 6, I think. Oh, okay. Well, now we're at 652,000 operations, nearly 700,000 operations, just to animate these guys. Now, keeping in mind that the 6502 processor, I think, is clocked at 1 million cycles per second, and it's taking me 652,000 cycles per second just to animate these guys. I've used up almost all my entire CPU power just to animate these guys. That's not good. That's why, if you play the games on the Apple IIe, they kind of didn't look that great, right? But the video games, they had help. The arcade games and the later consoles had help. They had what's called Sprite hardware, and they also had tile hardware. They basically had hardware tuned specifically to handle the updating of the frame buffer for you. Okay, and I'm lying too, because they didn't actually update a frame buffer either, because the video was so, the video RAM frame buffer, what would be static RAM, which was usually used in video, it was so expensive, it would be outrageously expensive to actually make a frame buffer. But they still had to update the screen, and they still use these pixels. And ultimately, what I'm trying to tell you is that the CPUs didn't do it. They had a lot of help. The CPUs actually had to know where Peter Pepper was, and he had to know where the other guys were, but they weren't responsible on the video arcade hardware and the later consoles for actually drawing all those dots. So I mentioned that the video game hardware had special hardware to handle drawing of these sprites and these tiles. So what exactly is a sprite and a tile? Well, a sprite and a tile are basically the same thing. They're just pre-done images. They're blocks, little rectangles that contain a bunch of pixels. They're usually fixed size, and those pixels are pre-drawn basically. So this is a sprite of the Burger Time character. And a tile is generally the same thing, except it's usually smaller. There's a difference between sprites and tiles, though, is sprites can generally be drawn anywhere to granularity of a single pixel. You can position this sprite at anywhere. If you think of the screen as an x-axis, if your resolution is 300 by 200, you could put one of the corners, let's say this corner of the sprite, at 0, 0, 0x by 0y. You could put it at 1x by 0y, 23x by 50y. Anywhere, any pixel, you can place a sprite. So you can put it with very fine granularity on the board. The tiles are laid out in a predefined grid, and tiles can be laid out only in certain positions. Kind of like a bathroom tile. They're basically stacked on top of each other, up and down, right and left, and they can't be arbitrarily placed on the screen. So each tile has a fixed location. So for example, in this Burger Time screen, this high score screen, these are all tiles. The tiles are aligned very fixed, right? It's very easy because whatever space this tile is, the B, you can put a B there very easily, and then right next to it you put an E and S, and everything's just aligned. It's like a grid. And the tiles are a bunch of pixels, usually a rectangle of pixels, and they're just placed in fixed positions. So it's very easy to lay this out. So tiles are usually used for, like, the text of things, high scores. For example, also the backgrounds. Oh, here, these are actually probably tiles also. Anything that's fixed is going to be a tile. And often the backgrounds are tiles. So things that don't move generally are tiles. So all these are tiles. All these stairs and the burgers and so forth and so on. But all the moving parts are actually sprites, right? So all the characters, if we play the game, all the characters would be a sprite. And all the Peter Pepper would be sprites. The enemies would be sprites. Everything else is probably a tile. So that's how it works. You have tiles for things that don't move, that are in fixed locations, and sprites for moving things that need to be aligned or moved in very small increments and placed wherever you want. And if you have MAME, again, I love MAME. MAME is amazing. You can actually, for most games, you can view the tiles and the sprites by hitting F4. Let's try that again. F4. There we go. F4, and then hitting the right square bracket. No, I'm sorry, hitting Enter. So these are actually my tiles, and I'm going to hit the right square bracket, and then I'm going to zoom in, and these would be sprites, right? Try to make these bigger so we can see them. There we go. These would be sprites, and you can see how the animation works. Each movement of the character is actually just like a little animation, or is a little separate frame, and you just draw these different sprites real quick, one after each other, as they move to get that animation. Like here's when a Peter Pepper gets hit by a bad guy. You can see this is, if you ever played the game, this is what happens. He kind of falls down on the ground and rolls around. And they have, it's just like an animation, a flip book. If you ever saw the old school way of how animation was done, so that's how it works. So how do you actually, in a video game though, how does the CPU say, hey, I want to draw a sprite or I want to draw a tile to the screen? Well, once again, MAME saves the day. If you watch my other videos, you see I often will use information from the MAME project to figure out things, or schematics, but usually I will look at the MAME project first, because why do the work of figuring out everything from the schematics, which is a lot more difficult or more time consuming, well, also more difficult, when I can just read it. So I go to the MAME project, get their source code. In this case, it's in their source directory, it's source MAME drivers btime.cpp, and find the address map. And here we see this looks good. Video RAM, range 1000 to 13FF. That's probably where how I interact with that video hardware. So what I'm going to do is I'm going to go ahead and pull up MAME with a debugger. So if you're remember, if you're familiar with this from my other videos, MAME 64 minus debug btime. I'm going to go ahead and bring it over to the screen here, and just to start running it with F5. Then I'm just going to move this, resize it. Yep. And I'm just going to hit I'm going to hit F8 once the game starts. F8 just pauses it. And so now I have this here. I'm going to shrink this down a little bit more if I can, and move this to the side. So I have the game paused, but the video hardware will actually still draw if I write stuff to memory. So I'm going to go to new memory window. I'm going to go to the address that I started off at, where it said the video RAM started off at 1000, and I'm just going to start writing values here. Let's start writing, I don't know, what should we write? 1 1s. So 1 1 1 1 1 1 1 1 1. Nothing's changing, which is odd, but it's not really. Often, well, you'll see. Hitting 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1 and boom, something has changed. And now if I do it, I see every time I add around 1024, when I start adding numbers, they're just going across the screen. So let's go over here to 1000, I don't know, let's start at this one, 1020, 0, 1, 2, 3, 4. Let's change that to a, I don't know, let's change that to 00. Oh, look at that. Disappeared. Okay, let's put that back to 1 1. Let's go back 2 more. 00. Oh, well, that's neat. Went away. So this address, 1020.021, probably is how you draw this tile location to the screen. The next one is this one. So let's do 01 here, 1024. Sorry, 1021. We got a 0 there. I did 01, it put a 0 there. I'm going to do 02, puts a 1 there. 03 puts a 2 there. 04 next. 05. So you get the idea, right? Um, this is, you can see how we draw tiles to the screen. And I'm just going to actually just keep hitting 1 1s. And look what happens. Isn't that interesting? Kind of skips over certain areas. That's because those apparently then are sprites. Often the game hardware will have, since the tiles are usually backgrounds, the when you have a background and there's a sprite over it, it usually the sprite takes precedence, and it does, it will show the background, but it'll show the sprite on top of it, so that you don't get this blocky factor. Like Peter Pepper here can be directly over text, and it doesn't get messed up. So there we go. We've seen now how we can draw sprites. All we got to, or tiles. All we got to figure out is where, how the addressing works, and you get the base address for MAME, and then just poke around. Let's say I wanted to write my name. I'm going to clear the screen here. I'll hit F3 to reset the game altogether, and then I'm going to stop it here. Let's go back to the new memory window. 0x111 or 0x1 and then 3 zeros, and let's just clear this. You can see that there's some values here. 42, 0, 0. The t goes away. All right, you see all these values going away. So you can see this is, if I wanted to draw rather than burger time. Let's put 42 here. Maybe not 42. Let's put 43. No. I want to put my name, Brian. So I just got to figure out what a B corresponds to. 41. 42. No. Let's try. Oops. 2B. No. 2C. 2D. 2E. 2F. A. So 30 is a B. All right. Often these values will actually be the ASCII values, but in burger time apparently it's not. So if I wanted to put an R, I just have to figure out what the code for R is. And if 30 is B, 31 is probably going to be C, right? 32, 33, 34, 35, 36, 37, 38, 39, 40. Okay, there's BR. And what was it, like 32? Nope. C, D, E, F, G, H, I, J, K, L, I, J, K. So I got to go back a couple. A, B, C, D, E, F, G, H, I, J, K, L. I have to go back, what, 4? So let's go back to 36, is it? Nope, 37 then. It's got to be 37. I'm not good with math. And we know that the A was, what was it? It wasn't 30, it was 2F and N. We just had N, didn't we? Let's go back to 3F. That's definitely not it. 2F. That's not it. 3A. Or almost. 3C. There you go. I wrote Brian on the screen. Get rid of everything else. And you can see how you can modify things and write them to the screen just by accessing memory. So tiles are easy. Generally with tiles, for every sprite, or I'm sorry, for every tile location on the map, on the board, there is a memory location, and you put a value in that, and it corresponds to one of the tiles. And you notice sometimes when I did things, different colors happen. So in burger time, it must be, and I really haven't looked at the burger time schematics or anything, but the tile, the value you put in the tile is not just the letter, but also encodes some color information, right? So cool. So that's tiles. Tiles are pretty easy. The other thing to realize about tiles is, notice how all I had to do was write a single byte to a specific video location to make the tile appear. That tile might be an 8 by 8 block of pixels, which would be 64 total pixels. I don't have to, like in the frame buffer method where I would have had to draw each pixel, that would have been 64 different writes to memory. In this case, because I had the tile hardware, all I had to do was run one single byte to memory, to a specific memory where I wanted the tile to appear. That's all the CPU had to do, and the video hardware took care of actually doing the displaying to the screen. So it had a huge savings advantage, 64 times speed up just to, or 64 times optimization just to write a tile with the video hardware. So I showed you how you can write tiles to the screen. Remember, tiles are just fixed images that can be displayed at specific fixed locations in a very specific grid. Sprites are very similar, but rather than having fixed data in fixed locations, they're fixed data, that is the little image, in any arbitrary location. So as with a tile, we're going to have to, say what thing we want to display, what tile or what image we want to display, but we're going to also have to give it other information. We're going to have to give it a X coordinate and a Y coordinate on the display to where to draw the tile. And sometimes you also have to give it attributes, like you want it flipped or rotated, so forth and so on. So let's see how this is done. I've got my MAME debugger up, and I've looked into, I haven't really understood or reversed engineered or read too much about, I don't know that it's published anywhere, the specific sprite information. So I just was testing by watching the screen run and looking to see, and we'll go ahead and do that, looking to see what's changing. So let's go to our memory location that we know the RAM's at. And I just started, as the game played, just watching what locations are actually changing. You can see we see some changing locations here, see some changing things here. And I just started poking around and seeing what happened. So what I've determined, and I'm going to restart the game here real quick, is that this game requires 4 things to be set to draw a sprite. It requires an attribute, which I don't completely understand yet, a sprite value, an index into the sprites, a horizontal location, and a vertical location. So what I discovered is that the sprite identifiers are located at 1x, where x is a number, a0. And there's a certain amount of them. I haven't figured out how many there are, but that's where you define a sprite. One of the sprites. So we're going to go to 1, 2, A0. Where is it? 1, 2, A0. And there's nothing there right now. Let's put in a number. 4D should be the burger time guy. And it's not going to show up right away. So I'm going to put in 4D. And then the attribute, I'm just going to set 1280. That seems to be an attribute that has to be set for the sprite display. Again, I haven't figured out exactly what that is. And then we have 12C0, which is the horizontal location. So let's just put it at 70. And 12E, which is the vertical location. Let's also put that at 70. And boom, look at that. We got a little burger time guy. I'm going to go ahead and move him up a couple pixels. Let's go move him up to 50. And maybe 40. That's good. I'm going to move him down to 45. I just want to get him, I'm really kind of weird. I want to get him centered nicely. There we go. Look at that. So that's all you have to do. All the computer has to do to draw this sprite. And this guy is probably, I think, 16 by 16 probably. I don't know. I didn't look exactly at it. But that's, 16 by 16 is what, 256 pixels? So to draw that, normally the computer, if it was drawing using the frame buffer method and the CPU is directly populating that video memory, it would have to have 256 writes to memory just to draw that. Here we saw all we need is 4. We need that attribute set, we need the actual sprite identifier, and then we need the horizontal and the vertical locations. And again, animation is just a series of changing these sprite identifiers. So I'm going to make him, I think, I'm going to make him go through the sequence of when he gets hit by the bad guy and, rolls around the ground. So it's 4D. The next, I believe, the next image in that animation is 4E. I'm gonna do it again because sometimes it doesn't update right away with the main driver here. Okay, yep, 4th F, 5O, 5-1, 5-2, 5-3, and it's gone. So we got 4D, 4E, 4F, 5O, 5-1, 5-2, 5-3. And that's how Sprite, that's how animation happens. It just happens real fast. I'm not, the computer can do that many times a second rather than me typing it probably once a second. So that's how sprites work. I also, as I mentioned, 1280 seems to be a sprite location. 1380 also is a sprite location. Let's put 6F there. I think that's Mr. Pickle. Isn't that right? Maybe that's not right. Thought that was right. Oh wait, I'm sorry. That's not that should be an attribute. It was 13A0 or 13A, yeah, A0. So 6F. Yep, and then let's draw this guy next to the Mr. We're actually I'm going to set Mr. I'm going to set the character back to his standing character, and let's just go ahead and then put the horizontal location. We can see already the pickle appeared at the screen because already there's zeros in his horizontal and vertical location. So I think we had him at 45 degrees or 45 over, and was it also 45 down? Maybe 47 down. Yeah, let's move him over to 40 over. Nope, we're getting farther away. Let's go the opposite direction. Let's make it 35. Or maybe not. There we go, 45. I maybe I was wrong. There we go. Okay. There we go. So he's right next to the. I'm gonna move him up to 46, and maybe 45. There we go. He's right next to the other guy there. So that's how sprites work. And you can see it's real easy for the CPU to draw. Rather than having to actually figure out each pixel and write it to the video memory, it just writes 4 numbers to the screen, and the video hardware takes care of it. All right, that's the lesson for today. Thanks for watching. Hope you enjoyed it. If you enjoyed it and you want to see more videos, please check out my Patreon site and consider becoming a supporter. And hey, if you support, send me a message on things you might be interested in seeing videos about. All right, take care.